Once again, mostly we will discuss today about confirmatory factor analysis, but before we start, I would briefly recap the discussion about path analysis, and we will finish our example, once again, replication of some published study. So, first of all, I would like to mention that path analysis is nothing more than a set of regressions that are only, I would say, chained together. So it means that one dependent variable from one regression could be independent variable from other regressions. And we know about some key terms we decided to use. So instead of independent and dependent, we are currently discussing about exogenous and endogenous variables. If we have a model as we have here on the picture, so endogenous variable is a variable into at least one-headed arrow is going into. So here we have at least y1 and y2 as two endogenous variables. And exogenous variables are those for which this rule is not valid. So it means there is no one-headed arrow going into these variables. So here we have x1, x2, and these two random arrows. So four exogenous variables. And once again, brief recap that if my variable is inside square or rectangle, we call this variable as manifest variable. So it means that this variable is present in my data set as the column. And if the variable is not included in my data set, in path analysis, these are only these random errors or disturbances, or sometimes only we call these as errors. So these are not present in my data. And if I use circles or ellipses, so we call these variables as latent variables or sometimes unobserved variables. So they are not present in my data. Classical unobserved variables are random errors. And also classical latent variables are factors in factor analysis we will be discussing later today. So there's only a brief recap about path analysis and division of variables into endogenous, exogenous, latent, and observed variables. And last time, if I go back into JAMOVI, we discussed about this model, so I will use this JAMOVI presentation of the final result, which was discussing that there is first one variable, which is defined as exogenous, which is social support. And then we have three endogenous variables: proactive coping, well-being, and depression. And this is the idea how this relationship could be formed. So it means social support is the only one predictor for proactive coping. Proactive coping together with social support are two predictors for well-being, and well-being is the only direct predictor of depression score measured by Beck's depression inventory. So that's our model. Here we have also some results that are computed by JAMOVI, and if we would like also to evaluate indirect effects, so first of all, we can briefly discuss which indirect effects are present in my model. So first of all, I can see that, for example, social support is not influencing directly depression, but it is influencing indirectly, and this influence is mediated by well-being. So this indirect influence of social support on depression is mediated by well-being, and mathematically it means that relationship between social support and depression could be computed as multiplication for both of these coefficients. So that's very easy, according to my opinion, to compute this coefficient. So for this case, I would be multiplying 0.33 by minus 0.48. So it's according to my opinion, approximately minus 0.15. sorry for that, 0.0015. And if I would try to evaluate such coefficient, so it means I would like to test this indirect effect, or I would like to compute confidence interval for such effect, it is not very easy. So there is no magic rule that, for example, t-test statistic for testing for this indirect effect is multiplication of t-test for individual effects that are direct, and also confidence interval couldn't be formed very easily. So there are some special formulas or approaches how we can evaluate these indirect effects, but once again, this is not very simple stuff, and that's why we would be happy if JAMOVI or our package Laban from R, which is behind the scene, will help us to evaluate these indirect effects. First of all, I will only mention how many indirect effects are present here. So from social support, it is like this one to depression, but also this one is also indirect effect for depression. So there are two indirect effects going from social support to depression. So once again, this way and this way. And there is also one more indirect effect, according to my opinion, and it is an indirect effect between proactive coping and depression, once again mediated by well-being. So this is the third one. So I expect if I would ask for indirect effects in JAMOVI, that JAMOVI will recognize these three indirect effects and will be able to evaluate these indirect effects. And one more comment to these indirect effects. Sometimes we can also discuss about comparison of direct effects and indirect effects if they are present both of these. So for example, if there would be also relationship for social support and depression here, so it means direct link, I would be comparing this direct link with two indirect links, and I would be concluding which one is bigger or stronger than the other one. Here, we do not have such case, so that's why we do not need to discuss these comparisons, as well as we do not need to sum up all these effects into one total effect. But in classical models for path analysis or some advanced models based on different regression models, we can sometimes discuss also about these difficulties. So first of all, we will once again run the model. So it means we will prepare this path analysis. And as a new step today, we will add this discussion about indirect effects. So once again, here we are. Once again, here we have our current model, and we will briefly discuss about computation and evaluation of these indirect effects. Once again, like these three should be present in my computation. So if you like to recap briefly how we can apply this model directly by clicking, so we can go into SEM and path analysis. And here we need to define endogenous and exogenous variables. So we have, once again, only one exogenous, so that's social support. This is only one exogenous covariate. And we have three endogenous, so well-being, depression, and proactive coping. And the next necessary step is to apply here by clicking into endogenous models to define predictors. So it means direct effects for individual variables. So for well-being, there is only there are two variables that are predictors: social support and proactive coping. For depression, there is the only one, well-being. And for proactive coping, that's only social support. So currently, we are once again computing this model. So once again, only one exogenous variable, social support, is present here. If I would like to have some more outputs, so I can ask for some more discussion Here, by parameter options, I can ask maybe for some more outputs, and the main output here is indirect effects, which is non-default. So if I ask for indirect effects, I would be expecting that there would be one more table, which would be including the evaluation of these indirect effects as we discussed previously. So here it is. So I can ask for these indirect effects. If you like, once again, you can ask for path diagram, but that's not necessary for us. So I would go directly into the output. So here it is, and there should be a new one table. I hope so, which will be discussing indirect effects. And here it is. This is table which has quite strange name, which is called define parameters, but we didn't define any parameters at all. It is automatically prepared by JAMOVI or by Blau-Duncan, which is behind the scene. And you can see here that indirect effect 1, how is it called? So it is labeled somehow, is going from social support to well-being to depression. From social support through well-being to depression. So this is the first indirect effect here. Second one is from social support through proactive coping, well-being, and depression. So this is this path. And the last one is from proactive coping to well-being to depression. So that's this part of the model. So these three, and I guess that this is the maximum of indirect effects we can define here. So that's all. You can also see here that here there is multiplication of previously defined parameters as P1, P2, P3, etc. So if you go back to previous discussion, here we should find, but it's not present here, so that's slightly inconsistent. So we should find here for this individual relationship description P1, P2, P3, P4, but once again, it's not present here, as you can recognize. But these individual parameters would be called as P1, P2, P3, P4. And these are multiplied here as we discussed previously. So for example, this indirect relationship could be computed, so it means the coefficient as multiplication of this coefficient and this coefficient. So that's it, how it works. And here we have results, and not only estimates, we know that's only multiplication, but here we have also the evaluation of so-called standard errors. Here we have also formal tests, so it means this small z is normally distributed variable, so it means values below -2 and above +2 are statistically significant. And here we have the evaluation by p-value, so it means that if we are testing individual indirect effects, as all these p-values are quite small one, so we can recognize that all these effects are, if we use, I would say, old language in statistics, are statistically significant. So for all of these, we would reject null hypothesis that there is no indirect effect. So it means this effect is at least not zero, but below zero or above zero. You can see that all of these effects are negative. By the sign, the reason why all of these effects is negative is very simple. As this is depression, I would say negatively oriented scale, and all the rest as well-being, proactive coping, and social support are positively oriented. So that's why all of these as final is depression every time. So that's why all of these are negative effects. And we can, for example, compare the indirect effect of social support and proactive coping on depression. So you can see that these two effects are quite comparable. So it means if I take this and this effect, so these two effects are comparable. And if you would like to compare total effect of social support on depression and total effect of proactive coping on depression, we should take these first two indirect effects and to make sum from these. And if I sum up two of these, as you can see, this one is a very small one. So you can see that these two variables, so it means social support and proactive coping, have nearly the same effect on depression as if I sum up the first two values and compare with minus 0.171. So it's totally comparable. So that's my final conclusion. So once again, I can sum up two of these as these are two indirect effects going from social support to depression. So if I sum up these two, I would get total effect from social support to depression. So that's it. If I would like to evaluate this total effect of social support on depression, so it means I would like to sum up these effects into one parameter, I would need to switch into general structural equation model. So I would go into SAM syntax. I would need to define classical path analysis model. And I would also need to define these two indirect effects and then define their sum as new one parameter. And JAMOVI would be able to evaluate this effect as well by similar table as we have here. But I would skip it. I guess that's quite easy to imagine how it works. So if you like to use indirect effects by SEM syntax mode, you need to define these individual effects by preparation of multiplication in your model. Only, if I remember well, in Lavaan language, if you prepare a new one parameter such as IE1, as it is here, it's not enough to type equality, but for these indirect effects or total effects, if I remember well, you should type following notation. I hope it would work. I will use some of these slides. So you should type AI, then this is equality sign for Lavaan, and then you should type, for example, P1 and P2 multiplied, if it would be like multiplication of two parameters. And previously in settings for the model, you should define that, for example, P1 is based on the logic that it is from social support to well-being. So you should define it is social support. Then wave, I'm not sure if I will type the wave, so sorry for that, but currently instead of wave there is some strange symbol on my keyboard, but tilde or wave should be here, and you should type P1 multiplied by, sorry for that, it wouldn't be not social support but proactive coping, and social support should be on the right hand side. So these notations would help you to define indirect effects by SAM syntax module. If you like to know more, please consult materials for Lavaan package. There is a very nice web page related to Lavaan package, which is written by the author of Lavaan package directly. So that's very nice to see how it works. So here we are, direct and indirect effects. And before we would go further, I would like to ask you to prepare your own computation of this step. So you would be replicating classical Blau-Duncan examples. So here is the model. Once again, X1 is education of the father, X2 is father's profession, X3 is son's education, and X4 is son's profession. And this is classical Blau-Duncan model. So that's, I would say, nearly classical path analysis, as you can see. And your goal would be to evaluate the model as a whole, Then if there are some indirect effects, please try to evaluate these indirect effects. Last one question is whether some of parameters here in the model could be the same. We know something about it from previous discussion about regression model for this Blau-Duncan example. So you should try to fix some parameters to the same value also. That's your goal. Currently there is 838, so I would propose 850. We would go back and we would discuss your results together with mine. Recording first of all, my question is if you try to apply this original Blau-Duncan example on original Blau-Duncan data, is it successful trial or not? What was the fit of the model? Does this model fit to the data or not? What was your result? I have here basic results of overall test, which is saying that my user model is following chi-square with 1.39 the value, 1 degrees of freedom, and p-value is 0.238. What does it mean? Can we apply this model or not? Yeah?
It means that it is appropriate.
Okay, so this model is appropriate. Once again, we are mostly using this chi-square test for simple models and for models with limited amount of data. So this is the case here. I must admit that I made a random sample from original Blau-Duncan big data set, which is approximately 20,000 cases. So here we have only a small piece of original data. So according to this chi-square test, this model is appropriate. If you go down and you discuss about SRMR, RMSEA. So all of these are quite nice. So it means these two, which are measuring, I would say, error of the model, are very low. So that's nice. And if you go down and you ask for some additional outputs, but it is present only as in structural equation models, you would also find quite nice results. So that's the overall evaluation of the model. And currently, I would go into the picture. So here we have the picture of our model. You can recognize that this is slightly different from our original picture, but mostly if we are applying path analysis model and we are preparing pictures somewhere outside of statistical package. Classical is the flow from exogenous variables to endogenous variables from the left to the right. So this automated style is not the best, as you can see, that my exogenous variable is totally inside the model. So it's slightly confusing according to my opinion here. But what we can see here is that we have here currently applied beta, so it means standardized coefficients. But once again, as these data, so it means this Blau-Duncan small data set is standardized, so it really doesn't matter whether you ask for coefficients, so it means unstandardized or betas standardized coefficients, as these coefficients are nearly the same. Standard deviation is close to 1 for all variables. And you can see that, for example, there is big impact for x1 and x2, 0.53, similar effect, and maybe one possibility to compare the effects would be also here. So it means x3, x4. That's not a big surprise, as this is about transmission of education to profession of the father. And here, the same effect for sons. So you can see 0.53 and 0.54. And according to Blau-Duncan model, we could maybe expect that these two effects are comparable, and maybe we could evaluate this coefficient only by one value, so we could fix these parameters to be the same. So that's one option in my model. Here I have maybe additional option also here, as you can see that from x2, once again, that's father's profession to son's education, and from father's education to son's education, these effects are close to each other, 0.33, 0.28. these are figures that are valid for my sample, and maybe it could be that for the whole population, these effects can be comparable. So maybe I can also fix these two parameters to be the same. What could be a result if I would ask for this one constraint and the second constraint? So it would mean that if I would go back to chi-square test, I would get 2 more degrees of freedom. So my model would get 3 degrees of freedom. Chi-square would somehow increase. That's by default necessary. And we would see the evaluation of this model with these 2 constraints, and we could evaluate this model. For simplicity, I decided for next steps, and then you can discuss your solutions only to take one constraint. So I only try to test whether these 2 relationships, so it means relationship between father's education and father's profession to son's education could be the same. So I decided to make only this one fixed parameter, and I can briefly discuss these results. So if I go down, so here it is. So there is one more fixing of parameters. I decided to apply this fixing of parameters in a structural equation modeling syntax mode. So here it is, and fixing is made by the same letter. So B letter is applied before x1, x2 in the second equation, which takes a relationship of x3 to x1 and x2. So that's one of possibilities. You know that alternative would be to assign different names to these parameters, and they make equality sign, but be careful, equality sign here with 2 equality signs as it is present in Lavaan language by this style. You can see it here, equal here is equality sign for constraining of parameters in Lavaan language. And if I would like to evaluate my current model, so you can see that my chi-square is slightly increasing, 2.1 instead of 1.3 previously. But here I have 2 degrees of freedom. And if for 1 degree of freedom, critical value is 3.84 or approximately 4. For 2 degrees of freedom, critical value is approximately 6, precisely, if I remember well from statistical tables, is 5.99. So this is still statistically insignificant result if we use old language for the evaluation of statistical tests. So it means that also this model, this equality constraint is fitting to my data. And my question is, once again, I apply constraint for these 2 parameters to be the same. If you try another constraint, and what was your result? Did you try some constraint? Not. Okay, so please, if you can, at least at home, try to apply the second constraint. So it means from x3, x4, and x1, x2 to be the same. It seems to me, at least to these values, that it will be successful trial, and that JAMOVI will recognize that this is possible constraint. So it means that the transmission from education to profession would be the same across generations. It would be a substantive result. So it is a possibility how we can slightly change the model. And here we have also the evaluation of indirect effects. So here we have 4 indirect effects. And all of these indirect effects, according to results, are statistically significant. So it means all p-values are below 0.05. But of course, that not all are the same strength. You can see that the first one, going from x1 to x4, is the weakest one, according to X estimate, and comparable to x1 mediated by x2. So these are 2 weakest. On the contrary, the next one mediated by x3 from x1 or x2 are much stronger relationships or indirect effects. And I would like also to add a small comment that if you would like to add these equality constraints, as we discussed, there are 2 options. you can use this structural equation modeling by syntax and use symbols such as B, the same symbols for two or more coefficients, or add some equality constraint on the next row. That's one option. But there's also one more option directly in path analysis dialog. So it means dialog which is based on clicking. And here under the path diagram, there is an option which is called custom model settings. And here, if you add to add directive, so here you can also add constraints to parameters. So it means by double equal sign, you can make these additional requirements. So that's also quite nice option. And if I go back to the comparison of this path analysis dialog and the next one dialog for SEM syntax, there is only one big difference. And this difference is based in the fact that for path analysis, there are nearly no evaluation of the quality of the model, which are present here in SEM syntax as additional outputs. So the CFIs, TLSIs, etc. are not present in path analysis. According to my opinion, the reason is that for classical path analysis models, we can usually apply a classical chi-square test, and there is no necessity to go to alternative indices. For general SEM, we are mostly using these alternative indices. That's why we can define these additional outputs. You can find these additional outputs here in output options. So here is additional outputs, additional fit measures options. And one, I would say, quite strange point which is present in the comparison of these two. So here we have the picture based on same syntax, and if you compare this picture to the previous one picture, so they are totally different. At least for the first insight, these are the same models, of course. But don't ask me why these two pictures are totally different if they are computed in the same package. So it means one in R. But SEM syntax and path analysis is preparing totally different pictures, as you can see, for the same models. Of course, substantively, they are comparable. I must say that this picture is still, according to classical structural equation modeling, much better than previous one, as at least n exogenous variables is totally on the left as the first one, and then we have on the same level 3 endogenous variables, and they are somehow linked. So that's it. And the same property is applied to all of these pictures. So you can apply for the picture with coefficients. You can add betas, so it means standardized coefficients here, if you like. You can add labels, if there are some labels present here. Here I have only B, and automatically P1, P2, P3, P4 is assigned. And of course, you can also ask for none, and there would be only picture with no information inside these arrows. So these are options for these pictures, and the same options, if I remember well, if I go back to this previous picture, are present also here in path analysis dialog. So here you can see coefficients, betas, labels, and none. So that's all. And you can also ask here for showing residuals here in the picture. So for all endogenous variables, you will add also residuals and their values. So that's it. And that's final step in path analysis evaluation. So once again, if I go back, so we confirmed Blau-Duncan model. Confirmation is maybe quite strong expression here, but at least we weren't able to reject this model. And we also discussed that these two coefficients could be the same. And once again, please try, these two are the same from x2 to x3 and x1 to x3. And please try also to find whether these two coefficients could be the same by another equality constraint. And last step before we would make a break, and after the break we would visit new topic. It means confirmatory factor analysis. I will only sum up some basic structural equation modeling rules. I will also upload for you the file which is announced here, which is called SEM6 rules PDF, which is including 6 basic rules for structural equation modeling from one textbook, and it is also reasoning in detail these rules. So we will only give some basic advice. So rule number 1 is saying that all variables that are independent, and we know that we wouldn't use mostly independent by exogenous. So for all of these independent variables are variances estimated. So for all exogenous variables, we are computing or estimating their variances. So here it is, as these small circles are every time related to all exogenous variables, as well as for random errors. It is slightly mixed in this picture for all endogenous variables, as all these random errors are also exogenous variables. So all variances of all exogenous variables are every time estimated by default. So that's the first rule for structural equation modeling. Fortunately, you do not need to remember this rule, as most of software packages that we can use for structural equation modeling are capable of this rule and know this rule and apply this rule automatically. So that's quite a nice property. Next rule is saying that if you have some independent variables, once again, exogenous variables, maybe better. So all covariances, so it means possible relationship, but by two-headed arrow, should be included in the model as estimated parameters. But we know at least that in some cases, this is not the best way how we would discuss about these phenomena. Maybe I would go briefly back, for example, to this picture. And if we would take this second rule as the finite rule, which must be valid in all details, it would mean that here we have one exogenous variable, which is social support, and we have also 3 more exogenous variables that are these random errors. And if I would follow previous rule number 2, it would mean that all of these, so it means social support and E2, social support and social support E1, and also all of these random errors should be linked together. So I would slightly modify this rule, that this rule is mostly valid only if I'm discussing exogenous variables that are manifest. So if I'm applying regression model, so it is mostly expected that these exogenous variables, once again, these will be predictors for dependent variable in regression, should be related by default. And for random errors, I would define slightly modified rule that mostly we do not expect that these random errors are related. So I would slightly modify rule number 2, that not all covariances between independent variables or exogenous variables, but I would say that all covariances for exogenous variables that are manifest are expected to be included in the model. I would like to say that this property, as we discuss this in detail, is usually automatically expected by software package. So you do not need to say that your exogenous manifest variables are related, but software is expecting and automatically implying this part into the model. And if you would like that these two should be independent, then you must define constraint that this relationship, so it means covariance or correlation, is at the value of 0. So if you would like to cancel this classical rule for structural equation modeling, you can actively make additional constraint to your model. So that's it for rule number 2, and I would say slight modification of this rule. Rule number 3 is saying that if you have some variables that are latent or observed, every possible relationship should be defined as regression coefficients. So, for example, if I go once again back to our previous model, here or here, it would mean that all variables should be linked together. But for example, you can see that here x1 and x4 is not directly linked by regression line. And the reason is, as you can see in the brackets, if theory is not expecting opposite. So here, Blau and Duncan didn't expect it that there is direct effect of father's education on son's profession. It is only mediated by father's profession and by son's education. There is no direct effect which could be theoretically present here. So I would say that in classical path analysis models or structural equation models in general, this rule is not applied fully, as theory is always expecting that some direct effects or some regression coefficients are not present in the model. So that's rule number 3. And these 3 rules could be applied mostly to path analysis. So that's why we are discussing these rules at the beginning. I can promise that next 3 rules that are mainly designed for confirmatory factor analysis, we will be discussing after basic introduction to confirmatory factor analysis model. So that's about these first 3 rules. And I would say about quite a lot of exceptions. If I sum up briefly, rule number 1 has no exception at all. So for all latent variables, for all random errors, and also for all other exogenous variables, I must estimate their variance. That's default. There is no option to reject this option. But for covariances, for exogenous variables, we usually apply this rule only for those variables that are manifest. And the next rule related to regression coefficients, once again, usually modified by the theory. So that's all about these first 3 rules that can help you at least to understand basic logic of structural equation modeling in general style. So that's it for this introduction.